Dehydrohalogenation, this is essentially undergoing an E2 reaction. It's essentially what we're looking at. A strong base will take off a proton from a carbon adjacent to a carbon with a halogen. In other words, here's our halogen, there's the carbon adjacent to it, and there's a proton. It can deprotonate it. Tertiary and hindered secondary halides give alkenes in great yields because they'd rather do a E2 than an SN2 for steric reasons. Tertiary halides are the best E2 substrates because they do not give SN2. So remember that from the chemistry of SN2. Tertiary things do not undergo SN2 due to steric hindrance of backside attack. So in order to do an E2 and to prevent an SN2, you have to use bulky bases. So the trouble with SN2 and E2 reactions are a lot of times you can get competing reaction pathways. You want to do the E2 reaction, but the molecules in the flask are doing the SN2 reaction, or they're giving you a mixture of products. So for example, let's say you had this and you want it to make this. Something like that. Well, throw in a base, right? Just no big deal. Throw in a sodium methoxide and methanol, boom. It should give you the alkene with no problem, right? Trouble is, say you get 60% of this. I'm just making these numbers up. But you may also get 40% of this. I don't know the numbers, but let's just say you get a contaminating product of the substitution. And you don't want the substitution. You want the alkene. Well, to fix that, you would use a bulky base. You would get a big old bulky base. Because remember, to do an SN2 reaction, you have to do what's called backside attack. The nucleophile has to approach from the opposite side of the leaving group. Well, normally, say for tertiary substrates, SN2 is not allowed, right? SN2 is not allowed because backside attack is prevented. No backside attack is allowed because it's just too much bulk behind the leaving group, too much stuff going on back there. So that's not going to work. So, but what about this case? This is a secondary halide. So here we have a secondary halide. So we're getting some SN2 reaction. We can't bulk up the substrate. We can't put more bulk around the bromide. But what we can do is put more bulk on the base. We can switch bases. We can stop using the small little thing here, and we can get gargantuan. Because a gargantuan base, a big base, a large bulky base, will prevent this from occurring because the bulky base will start getting tangled up inside of these carbons before it can attack the electrophile. And what are some examples of bulky bases? Well, the most common one, or one of the better ones, at least in my opinion, is T-butyl alcohol. Or T-butoxide, excuse me. T-butoxide has a big old bunch of bulk here. Here's the basic ion. Here's the ion that's going to do all the work, the O minus. And here's the baggage that it's carrying around. This baggage will get tangled up in this ring system before the oxygen can touch that carbon, or at least slow it down so that it prevents this from occurring. So using a bulky base is good if you want to promote E2. Other examples of bulky bases. Triethylamine. There are numerous, by the way. 2,6-dimethylpyridine is another example of a bulky base. But now, the take-home message is not the names of these things. The take-home message is the bulk, the sheer amount of carbons that are behind these atoms. The nitrogens are the basic elements here. That you have so much bulk around those basic components that the basic component, the nitrogen that needs to attack the nucleophile, that needs to attack the electrophile, just can't get there That's what the bulk is doing. That's exactly what the bulk is doing. It's preventing attack on that carbon, forcing the molecules to behave as bases and attack these protons. Now these protons, remember, are hanging out there. The carbons are more in the middle of the molecule. The hydrogens are on the outside of the molecule. So if you want, you can think of the hydrogens as the rind for an orange for example. Imagine the molecule is an orange. The hydrogens are the skin of the orange. The carbons are the fruit on the inside. Think of it like that. So the rind is easier to get to, is what I'm trying to get you to think about. So now let's imagine we have this molecule here, and we're going to do an E2 on this molecule. If we do an E2 on this molecule, there's potential for two different products. There's potential for this product, or we could also form you have potential for two products. You can form this one, the most substituted double bond. This is known as the Zaitsev product. Remember, Zaitsev's rule says when given the chance, an elimination will form the more substituted double bond. This is known as the Hoffman product, the least substituted product. Now, what if you want the Hoffman product? What if you want to have it? Well, that's where the bases come in, right? A bulky base favors Hoffman. A bulky base will favor the Hoffman product. A small base will favor the Zaitsev product. So bulky base, Hoffman. Small base, Zaitsev. And that's how it works. Now, why would a bulky base give me the Hoffman product? Why is that? Well, let's think about the mechanism here. Let me clear my board here so I can make some room for a mechanism. Let's think about mechanism here. In order for an E2 reaction to occur, the base must attack here, and they fall in like that, and the bromine comes off. That's the Hoffman product. Or the base, and let's draw another molecule here. Or the base has to come in from over here. That will be the Zaitsev product. Well, the Zaitsev product is the more stable product. The Zaitsev product is the more stable product, so they typically want to form. But you have to have collisions first. Now, remember, molecules aren't thinking. They're only reacting. So if the base just simply cannot collide with this hydrogen, this reaction is not going to happen. Or if the base collides with this hydrogen less, this reaction will happen less. If the base can collide with these hydrogens more, the reaction will happen more. Think about this for a second. If you're big and bulky, and you try to get into a small hindered space, you probably will get in there. It's just going to take you time to figure out the approach vector to get in there. So imagine you're a big bulky base trying to get at that proton right there. In order to get to it, you have to get around this methyl group somehow. Now, I know people don't think methyl groups are very large, and in fact, they're not all that large, but they're still there. They're still fairly big. So to get here, I have to get around this. Now, remember, I'm a negative thing. I'm just looking for delta positive. All these bad boys here are delta positive. I can just attack them. So I'm going to bang into these bad boys a whole bunch. And this reaction is going to occur a lot faster if I can't get in here. Now, if I'm a small base, I can get in here a lot. Small bases can get in here a lot because they can just circumnavigate around that methyl. So big bases have a hard time colliding at the internal hydrogens because of sterics of the rest of the molecule. The rest of the molecule blocks them. They'd rather attack these ones on the outside, these methyl groups that are further out. They're far away from all the other bulky nonsense that's going on, so they're going to attack there. And that's why you get a Hoffman product versus a Zaitsev product when you have a big, bulky base. The bigger and bulkier the base, the more likely they're going to attack out here because they simply can't get into here. They can't collide with it.